Welcome everyone to our presentation on some IDE-based editing support for embedded feature annotations. This is joint work by a couple of authors, but the main work was done by Johan Martinson and Herman Jansson, who did this as part of their master thesis, and they produced a plugin for IntelliJ that I would say is one of the tools with the highest TRL levels I think we've ever produced in the context of our research. Was supervised by Mukelabai, my PhD student, Alexandre, Bergel, Truong, Ho-Quang, and me. The main problem we are addressing here is the so-called feature location problem. And feature location is one of the most common tasks of developers. You try to maintain a feature or evolve a feature, and for that you need to know the location of that feature in code, which is especially challenging in large code bases. And when features are scattered over the code base. In particular, this problem is difficult in very rich systems. Often you not only have to create one variant of a system, but many different variants of the system. What organizations are often doing is to create clones of systems and then adapting them to the customer needs or adapting them to the environment. And this strategy is typically called cloned own. Now, you sense it, this often doesn't scale with the number of variants. So when you can't maintain all those cloned variants anymore, you need to reintegrate those variants into an integrated platform by decomposing your variants into smaller parts, which we often call features. And then by selecting the right features, then you can often automatically derive the individual variant. And of course this needs re-engineering, and in this re-engineering you need to identify the features that are in your code, and you need to of course also locate them. Now, in the research community there was often a lot of focus on the latter part, on integrating or improving already integrated platform. But companies, they spend most effort by doing their clone own. I mean, you have the most skilled developers managing these clones by integrating and copying code back and forth. So we want to support this more clone own oriented style of development here. And here we want to support traceability, and it's important to understand that traceability is somewhat different from verbability. Let's imagine we have two clones, classes. Integrate those classes into one platform. So here's an example from a Linux kernel. Let's say we have a feature. It's called init. It has a method. And now it is forked. Someone created a clone and modified it. And you can see that there's one line modified here. Its first line in the method is now ACPI boot init. So if you want to save the information that the feature init is in this method, then you would somehow annotate this this method here with some traceability annotation, or record it somehow. Now if you integrate this into an integrated platform, what you do is you wrap the differences in so-called if-defs, and these if-defs, they are verbability annotations. Okay, so traceability means that we want to trace all types of features, whereas with verbability annotations you only want to record differences between products. Okay, so it's one of the core differences here. Now for recording traceability, we basically have two strategies. You can have the lazy strategy. This means that you recover traceability information only when you need it, so when you need to evolve or maintain a feature. You can follow the either strategy, which means recording and editing traceability information during development. This is the strategy that we aim at in this work. And the idea is that, well, when you write some code, then you often have a feature in your mind that you want to record, that you work on. Now, one could think about automated traceability recovery strategies, if you call it lazy strategy, there has been a lot of work on so-called automated feature location. There's some service about that, but the problem is that all those tools, they have a low precision and require a lot of manual effort. So they're difficult to set up. You have to provide seeds to features. You have to set up the tools for your environment, and then often they give you too many false positives to be useful. And also manual feature location, there have been experiments that show that locating one feature can take easily up to 10-15 minutes in some relatively small systems already. So our focus is on recording traceability information early and during the development with embedded annotations.
I'm now going to introduce how to leave these embedded feature annotations or traces in the code so that you can create your map. During this presentation, we're going to use the example of a simple snake game when talking about code and traces. And to your left, you can see the file structure of this game. It has 3 different folders: the graphics folder, the logic folder, and the Pojo folder. Although we will demonstrate this notation in Java files, the syntax can be used in any programming language that supports comments. The central part in mapping code to features is a file called the feature model. This file lists all the features that are present in the software. For example, you can see that there is a feature called tile that has sub-features called poison and food. The file shows this hierarchy of features in a tree model. In order to say that a particular piece of code relates to a certain feature, there are 4 different ways to specify this. One way is to use a file called the featured folder. This is a way to say that, for example, the feature playing area relates to all the code within the current folder, including its subfolders. Another way is to state that a feature relates to a certain file. In this case, the featured tile is related to all the code in the file square panel with Java. Users can also map bits of code to features. This can be achieved by either block or line annotations. A block annotation specifies that all the code between the begin and the end tags are part of the feature. Line annotation achieves the same thing, but for a specific line of code. You may notice that the line annotation looks a bit different from the others. The reason for this is that the feature called spawn is defined in 2 different places, both for poison and for food. To make sure that the correct spawn feature is referenced, it has to be defined with its parent. In this case, the parent of this spawn feature is food. So, our solution to these problems is HAnS, helping annotate software. It is implemented as an IntelliJ plugin, and the reason for that is IntelliJ is a popular IDE, but also when implementing a plugin for IntelliJ, it is also automatically created for PyCharm and Android Studio and other JetBrains IDEs. First of all, we're going to talk about the mapping features of HAnS, and then follow with browsing features and refactoring features. The mapping features concern the syntax of the notation that we have discussed previously, the code completion of that syntax, live templates, which helps speed coding up, and surrounding live templates. As you can see in this video, we're going to start by mapping this line of code to the spawn poison feature. And it's quite easy. You just write and L and it will continue with helping you with the code completion. Then you can mark the code, right click and surround the feature with a feature annotation. So now we surround that with a block, we surround that block of code with a new annotation, thereby mapping this entire block to the poison feature. Browsing features concern more about how you locate these features that you have mapped. So we have the feature model view, find usages of that feature, and the syntax highlighting. All of these help with finding the traces of features. What you can see in red here is the feature model view, and it has some different functionalities. For example, we can find all of the usages, and here we can see then we can find all of the usages of the food feature, as well as seeing that it is syntax highlighted. So to the refactoring features. This concerns renaming a feature or adding and deleting a feature from the feature model. Here we can see the support for refactoring. So pay attention to the feature blank. We're going to try to rename this feature. And you can simply do this by right-clicking, clicking rename, and then type the name you want, in this case background, and then it will search in the files of the project and rename it to background. This also handles conflicts. So if there were another feature called background already, it would rename all of the background features to also have its parent's name. So you would always be sure that a feature is named uniquely. The development and evaluation of HAnS was done using a design science methodology. This means that the plugin was developed in multiple iterations. In our case, we used 2, where we developed the plugin and then evaluated it, only to restart and develop it further, followed by a second evaluation. For the evaluation of HAnS, we conducted user studies. In order to test HAnS on a real example, we used the snake code that we have used as an example during this presentation. At the beginning of the user studies, the participants were given a short introduction to embedded feature annotations and the HAnS plugin. They were then tasked to perform 2 sets of different tasks where they implemented features and annotated them. The participants were divided into 2 groups, where one group performed the first task set with HAnS enabled and the second task set with HAnS disabled. The second group did everything in the opposite order. The idea behind this was to mitigate the risk that the order of using the plugin would skew the results. We also asked the participants to record their screens so that we later could check that they performed the right tasks and how they navigated in IntelliJ. After finishing the tasks, they were asked to answer a questionnaire with questions about their perception and thoughts about the plugin. All results we present are a subset of the results that we have gathered. These specific results are chosen as they give a general representation of what the participants answered. To find out which features were needed for the tool to be considered effective, we listed in a discussion group these basic functionalities: EVA syntax support, code completion, syntax highlighting, and a basic version of the feature model view. This was also the functionality that we used during the first user study. These quotes sum up what the participants said in the questionnaire during the user study, and together with the elicitation with the discussion group, they help answer which features are necessary for us to consider the tool to be effective. To answer the second question, is the tool effective? We have to see how non-intrusive the plugin can be to a developer. Do they find it less time-consuming to annotate code with the plugin? And does it help them with locating features? And as we can see from this result, they generally find it less time-consuming to do these tasks with the plugin. However, less time doesn't speak for itself. Increasing the speed of a task often increases mistakes. And therefore, we recorded the mistakes. We asked the participants to record their screens, as you might remember. And by doing this, we could then go back and look at the different kinds of mistakes. So we can see here that there are three different kinds of severity to these errors. And the feature reference error, syntax error, and the spelling errors are of a high severity, because if you do this mistake, it would take you a long time to fix that error, and that would defeat the purpose of the plugin. The reason that the definition of definition error, well, it's created when you define a feature, is just medium, is because if you just make the mistake at the definition level and not in the rest of your code, it is quite easy to fix. It's just one file. However, it can still be very cumbersome to fix depending on the size of the project. So does this result actually create a usable and effective plugin? To find the usability of the system, we asked the participants questions and graded them with a system usability scale. If a number is above 70, it means it gets a possible grade. Above 76 is good, and above 87 is exceptional. Overall, the scores are above 70, and the total score for the plugin is above 76. We can therefore deem the plugin to be at least possible. The only score lower than 70 is I felt very confident using the plugin. And we think that this can be explained by the word very. To be very confident with the plugin, just having used it for a couple of minutes, maybe hours, it's not strange that they don't feel very confident using the plugin.
So yeah, now that we know that you can become quite efficient with the plugin, that you can add your annotations, your development efficiently to the code. Once you have those annotations, you can of course also provide different tool support to the developers that gives another immediate benefit. For instance, in terms of visualizations. So you can visualize the features and their locations using different diagrams, as we show here. You can also show metrics per feature that show you perhaps what is the biggest feature, what is the most scattered feature, what is the feature that is tangled with many other features, and so on. So here's some other tool support that we've developed in our research. Most of them are not as mature as, I would say, this IntelliJ plugin, but yeah, the idea is always to give the developers some immediate benefit to further encourage them to use these annotations, because at some point, I mean, there is some extra effort to add those annotations. We've also done some case studies where we've tried to understand the cost and the benefit of using these annotations. And the cost is relatively low. And you also don't often have to maintain those annotations, because they often evolve naturally with the code. If you move some code around, of course the annotations they survive. And the benefits for avoiding feature location effort, as we discussed at the beginning, is relatively high. So in summary, in this presentation, we've just discussed the feature location problem. We've discussed embedded feature annotations to address the feature location problem. We've presented the HAnS plugin, which is of course available open source. And we briefly looked into further tool support. And this concludes our talk. Thanks for listening.